Let's solve a problem from an old exam question related to equilibrium and stoichiometry. So this is the question that we're looking at. Read the question yourself and try to answer it yourself before you continue with this movie. So here we have the equation of the Haber process, which is being asked about in this question. And the question says that initially, that means at the start, we have 4 moles of nitrogen. So let's record that. We start with 4 moles of nitrogen, and we have an unknown mass of hydrogen, and let's call that unknown mass X. So mass is measured in grams, and we need to find out what is the mass in grams of hydrogen that we had at the beginning. But for consistency in this table, let's refer to moles throughout. We also don't know how many moles of hydrogen we have. So we could say X mole, or change it to Y mole if you like. All of that is sealed in a 2 decimeter cubed flask. Remember that when we get to concentrations, that value is going to be important, that volume. And it's allowed to reach equilibrium at a constant temperature. So when we start off, we only have the nitrogen and hydrogen, so there's no ammonia. And this is all sealed, so we cannot get gases escaping or entering. But we know that this reaction is reversible, meaning that the nitrogen and hydrogen are going to react in the forward reaction to form some ammonia. So there is going to be some ammonia formed. Some ammonia is going to be added to the vessel from the nitrogen and hydrogen reacting with one another. And we're going to have some ammonia as a result once we reach equilibrium. Actually, even before that, as soon as the 2 reactants start reacting with one another. We also know that obviously that ammonia cannot come from nowhere. It came from the nitrogen and the hydrogen reacting with one another. So that means that we must get a decrease in the amount of nitrogen and hydrogen during the reaction process before we reach equilibrium, so that that can turn into some ammonia. So during the period of time when we do not have equilibrium, the forward reaction is going to be greater than the reverse because we're going from some reactants and no products. And so obviously the reactants first have to react with one another to produce any product at all. So the forward reaction is going to initially be greater than the reverse reaction. But as the ammonia gathers, the reverse reaction will increase in magnitude until the 2 of them are equal to one another. In other words, until we reach equilibrium. And once we've reached equilibrium, the rates of forward and reverse reactions will be equal to one another, and then the number of moles of nitrogen and hydrogen and ammonia will not change over time. But of course, we don't yet know what those amounts are. Let's carry on reading the question. At equilibrium, we have a concentration of ammonia of 1,5 mole per decimeter cubed. That doesn't mean we've got 1,5 moles of ammonia. So now we're losing some consistency in our table because before we were only speaking about moles. Now I'm giving it in concentration because that's what the question gives. 1,5 mole per decimeter cubed. Mole per decimeter cubed is the same thing as molar. So instead of writing mole per decimeter cubed, we could rather say capital M molar. But that molar doesn't mean mole. It means mole per decimeter cubed. Let's carry on reading. Calculate the initial mass of hydrogen. So we want to find out how many mole of hydrogen and then convert that into mass. In other words, how many grams of hydrogen. That is what the question's asking us. If the equilibrium constant Kc at this temperature is 1,8. Okay, so how are we going to make progress in this? The first thing is that we need consistency in our table. And we don't have consistency because here the information is concentration, whereas here we have number of moles. So let us convert this concentration and find out from it how many moles of ammonia we have at the end. So we know that concentration is equal to the number of moles divided by volume. And we are trying to find the number of moles of ammonia that are present at equilibrium. In other words, when our concentration is 1,5 mole per decimeter cubed. And we are given the volume of the flask, it's 2 decimeter cubed. So we simply need to substitute those values into our equation and solve for N. So N is equal to concentration multiplied by volume. The concentration of the ammonia at equilibrium is 1,5 mole per decimeter cubed. And we multiply that by the volume. The volume of the flask, and therefore of the ammonia at equilibrium, is 2 decimeters cubed. cubed. So we multiply 1,5 by 2. Notice the decimeter cubes cancel, and we're left with moles, which is what we want. We want the number of moles n. 1,5 times 2 is equal to 3 moles. So at equilibrium, we have 3 moles of ammonia. Where did those 3 moles of ammonia come from? Well, they were formed during the reaction. Where were they formed from? They were formed from some of this initial 4 moles of nitrogen reacting, decreasing the amount of nitrogen present. And of course, they also needed to be formed from hydrogen. They were formed from some of these X moles of hydrogen reacting, decreasing that. So now our question becomes, well, how many moles of nitrogen were needed to form these 3 moles of ammonia? And how many moles of hydrogen were needed to react to form these 3 moles of ammonia? And so that's a sub-question that we make for ourselves. Now we know that the reaction ratio is 1 mole nitrogen for every 3 moles of hydrogen to produce every 2 moles of ammonia. That's the reaction ratio. And we can apply that reaction ratio to this particular question. So we ask ourselves, how many moles of nitrogen were needed to react to form 3 moles of ammonia? So that's our particular question. We now apply the reaction ratio which we know from the balanced equation to make our equivalent values that we use in our conversion factor. We need mole of ammonia at the bottom to cancel away mole of ammonia that we have in our question, and we need mole of nitrogen at the top to introduce our required unit. And we know that the reaction ratio between them, as given by the balanced equation, is that we need 1 mole of nitrogen for every 2 moles of ammonia that are produced. So our answer is 3 divided by 2, which is 1,5 moles of nitrogen. We need 1,5 moles of nitrogen to produce 3 moles of ammonia. That makes sense because the ratio in which they react is 1 mole nitrogen for every 2 mole ammonia. So if you don't want to form 2 moles of ammonia, but rather 3 moles of ammonia, we need half as many of that, 1,5 moles of nitrogen. Now what about hydrogen? How much hydrogen must have reacted to form 3 moles of ammonia? We know that the ratio in which they react is 3 moles of hydrogen for every 2 moles of ammonia produced. So our question is, how many moles of hydrogen must have been reacted in order to produce 3 moles of ammonia? We apply the reaction ratio which we get from the balanced equation to this specific situation. We need moles of ammonia at the bottom to cancel away the given unit. We need moles of hydrogen at the top to introduce the required unit. And we know from the reaction ratio from the balanced equation that for every 3 moles of hydrogen that reacts, that produces 2 moles of ammonia. So therefore, if it's rather 3 moles of ammonia that are needed to be produced, we need 3 times 3 divided by 2, which is 9 divided by 2, 4,5 moles of hydrogen to react. So we put that information into our table. We know that it must have been 1,5 moles of nitrogen that reacted with 4,5 moles of hydrogen in order for us to produce 3 moles of ammonia. And we know that in the reaction process, the 4 moles reacted. They were not produced, they reacted. So that decreased the amount of nitrogen that was present. The hydrogen reacted. It was not produced. So that decreased the amount of hydrogen present. Whereas the ammonia was produced. That increased the amount of ammonia present. So we can simply do the sums, and 4 minus 1,5 gives 2,5 moles. That means at equilibrium there must have been 2,5 moles of nitrogen. We don't know what X is, so we cannot yet do this calculation. In fact, we're going to rather do the calculation backward to find X. How? Well, now we know the equilibrium amounts of nitrogen and ammonia. If we could just find the equilibrium amount of hydrogen, then we could do that backward sum to find out, well then, how many moles of hydrogen must have been present at the start. But how can we find this number of moles of hydrogen at equilibrium? By using the equilibrium constant. Because remember, we're given the equilibrium constant as 1,8 for this reaction at this temperature. What does equilibrium constant mean? It means the ratio of the concentrations of the products to reactants, as long as we raise each concentration to its power in the balanced equation. So for the Haber process reaction, that means Kc is equal to the concentration of ammonia raised to the power 2, because that's the coefficient in the balanced equation, divided by the concentration of nitrogen, not raised to any power because, well, raised to the power of 1, because 1 is the coefficient, multiplied by the concentration of hydrogen raised to the power 3, because that is the coefficient in the balanced equation. We already know the concentration of ammonia. It's given 1,5 mole per decimeter cubed at equilibrium. We don't know the concentration of nitrogen, but we can calculate it. We've got all the information needed to calculate it. We don't know any information that can help us yet directly to find the concentration of hydrogen, but then there is only one unknown, and so we can solve for it in this equation, and that's what we're going to do. But before we do that, we need the concentrations, not the number of moles at equilibrium. So we already have that for ammonia, but as I've already said, we don't yet have it for nitrogen. We have the number of moles of nitrogen, but we can calculate it because we know the number of moles and we know the volume. So we can make use of this formula to calculate the concentration. Concentration is equal to number of moles divided by volume. The number of moles we've already calculated is 2,5 moles, and the volume is 2 decimeters cubed. 2,5 mole per 2 decimeter cubed is equal to 1,25 mole per decimeter cubed, molar. So now we have the concentration of nitrogen at equilibrium, as well as the concentration we anyway had of ammonia. All we need is to calculate the unknown here, the concentration of hydrogen. So we simply substitute all the values that we know into our formula. We know that ammonia's concentration is 1,5 mole per decimeter cubed. Don't forget to raise that to the power 2 to square it. We've just calculated the concentration of nitrogen at equilibrium. It was 1,25. We don't need to worry about raising it to any power. And we know that Kc is 1,8. So we have one unknown value here, the concentration of hydrogen. We need to manipulate this equation, though, to solve for the concentration of hydrogen. How are we going to do that? Perhaps the easiest way to see it is that this is also a fraction, 1,8 over 1, and we're going to cross multiply. We're going to multiply 1 by 1,5 squared, and we're going to multiply 1,8 by all of this. So there we've done that. So here we've multiplied 1,8 by 1,25 and by the concentration of hydrogen raised to the power 3. And all of that is equal to 1,5 squared. So how do we proceed? We want the concentration of hydrogen raised to the power 3 on its own. So how do we get it on its own? We must divide both sides by 1,8 times 1,25. Remember, what we do to one side, we have to do to the other side, otherwise it's not legal. And when we do that, this side clears, leaving the concentration of hydrogen cubed on its own. So that's what we've done here. So now we can get out our calculator, and we type in 1,5 squared, divide by, open bracket, 1,8 times 1,25, close bracket, equal. And we see that the answer is 1. So the concentration of hydrogen cubed is equal to 1. But we want the concentration of hydrogen, not cubed. So we need to cube root 1, which is obviously equal to 1. But let's do it on the calculator anyway to confirm. So here we cube root 1 equals 1. What have we been finding out? The concentration of hydrogen. What is the unit of concentration? Molar, capital M, which is the same thing as mole per decimeter cubed. So here we have the concentration of hydrogen at equilibrium. Now, in order for us to find what the number of moles of hydrogen were at the beginning, we don't want concentration here. We want the number of moles so that then we can work backwards to what the number of moles must have been at the beginning. So we need to now convert this concentration into its equivalent number of moles, remembering that the volume of this flask is 2 decimeter cubed. So how do we do that? We again make use of this relationship and we're trying to find N. We know the concentration, we've just calculated it, it's 1 molar, and we know the volume, it's in the question, it's 2 decimeter cubed. So it's a very simple calculation. We simply multiply 1 mole per decimeter cubed by 2 decimeter cubed. Notice how decimeter cubes cancel and we're left with mole. 1 times 2 is 2 mole. So now we know that there were 2 moles of hydrogen present once equilibrium had been reached. Previously, we had already calculated that 4,5 moles reacted during the reaction process, decreasing the amount of hydrogen by 4,5 moles. So how much must have been present at the beginning if, once you take away 4,5, you're left with 2? Can you see what the answer is? In case you needed an equation form, x minus 4,5 must equal 2. So what must x be? Solve for x. X must have been 6,5, so that once you take away 4,5, you're left with 2. But be careful, we haven't finished yet, because it asks, calculate the initial mass. And mass is not measured in moles. Mass is measured in grams. So we still need to convert this into its associated number of grams. So you might want to use this formula to help you to do that. So we are trying to find the mass in grams. We have the molar mass. Now be careful there. Here from the periodic table, we have the molar mass of hydrogen H as 1 gram per mole. But remember, we are dealing with H2, and so the molar mass is not 1 gram per mole. The molar mass of H2 is 2 grams per mole. And we know the number of moles, it is 6,5 moles of hydrogen, and we need to then find from that the number of grams of hydrogen. It's obviously going to be double 6,5, but let's do the calculation anyway. We can do it simply by substituting into the equation. Let's do it that way. M is equal to N times capital M. Substitute 6,5 moles times 2 grams per mole. That gives us 13 grams. Let's also do it with the unit factor method. We want to know how many grams of hydrogen do you have when you have 6,5 moles of hydrogen, H2, and we know that 1 mole of hydrogen, H2, has a mass of 2 grams, and therefore 6,5 moles of them have a mass of 13 grams. Doesn't matter which method you use, we see that is the final answer. So let's just quickly look back. What have we done? Right in the beginning, we were given this information, 4 moles of nitrogen. We were not told directly 0 moles of ammonia, but the question implied it, because the question said we only put in nitrogen and hydrogen. So then obviously that means there's no ammonia in the beginning. And then we were also told that the final concentration of ammonia, once it reaches equilibrium, is 1,5 mole per decimeter cubed. The other piece of information we were given is the volume, 2 decimeter cubed, of this enclosed flask, the sealed flask. And the last piece of information was Kc, which is 1,8. And what we had to find was the mass of hydrogen present. Later we found that it was 13 grams, but we didn't know that at the beginning. We didn't know how much hydrogen there was in the beginning. Those things circled in red are what we started with, and the one that we've circled in blue was where we needed to end. Now, how did we go from the red circles to the blue? Our first step was to find out how many moles of ammonia there were at the end, so that we could work with moles throughout. So that was a simple conversion from the concentration that was given, making use of the volume. So if we know that the volume is 2 decimeter cubed and our concentration is 1,5 mole per decimeter cubed, the number of moles we have must be double 1,5. So then we knew the amount of ammonia that was present at equilibrium. Therefore, we knew that that's how much ammonia must have been formed, because it had to be produced since there was nothing at the beginning. And that helped us to then work out, well, how much nitrogen and how much hydrogen must have reacted in order to form those 3 moles of ammonia. So we applied the reaction ratio, 1:3:2 moles, to this particular situation, and from that we found, well, then it must have been 1,5 for 4,5 for 3, because those are still in the same ratio as 1:3:2. So once we knew that, we could then calculate the number of moles of nitrogen at equilibrium by simply going 4 minus 1,5 equals 2,5. So now we had the number of moles of nitrogen and the number of moles of ammonia that we had at equilibrium. If we could just know the number of moles of hydrogen that was also present at equilibrium, we could work backwards to find the number of moles of hydrogen there must have been at the beginning. So how do we find that number of moles of hydrogen? We make use of the Kc value. But before we can use the Kc value, we had to convert the number of moles of nitrogen at equilibrium into its concentration, because Kc makes use of concentration. And we know, of course, that the volume is 2 decimeter cubed. Therefore, the concentration must be half of 2,5, 1,25 mole per decimeter cubed. That was the concentration of nitrogen that we had at equilibrium. So now we knew the concentrations of nitrogen and ammonia that we had at equilibrium. We plugged those numbers into the Kc formula and solved for the unknown, which was the concentration of hydrogen. Since we know the volume of hydrogen and now the concentration, we could calculate the number of moles of hydrogen. Once we had the number of moles of hydrogen at equilibrium, we did that working backwards that I referred to earlier, and we calculated how many moles of hydrogen must have been present at the beginning, and then all we needed to do was to convert that into grams. I suggest that now you stop the movie, try the whole procedure yourself, and then watch the movie again and see if you managed it yourself.